Welcome to the amazing world of helicopters and the challenges of vertical flight. In the next hour, we'll look back on some of the remarkable and often bizarre inventions of the aviation pioneers who pieced together the puzzle of controlled vertical flight. We'll take you from heli-contraptions to practical flying machines. A top test pilot will show you exactly how they fly. Then we'll follow the evolution of the helicopter into a new breed of hybrid aircraft. And we'll be the first to get a close-up look at a 21st century virtual reality stealth fighter like nothing that's ever flown before.
Weapons on, lasers on.
Stay with us. From hovering insects to sci-fi reality, we'll look at man's fascination with vertical flight. Join us as we explore the science and technology that created the phenomenon of the helicopter on Helicopter Tech. The helicopter is a technological and aerodynamic marvel. But if you think about it, it is an odd-looking creation that would seem to defy all the laws of natural flight. It has no wings. It often looks more like a giant insect or even a flying banana. It is easy to imagine the earliest humans gazing into the sky with dreams of soaring through the heavens. Slowly, man unlocked the secrets of flight, culminating in that most remarkable feat in aviation history, the primitive flight at Kitty Hawk in 1903. While the Wright brothers were fulfilling the vision of those who dreamed of flying like a bird, some found their inspiration in the flight of other creatures. They looked at nature and saw dragonflies hovering, the vertical takeoff and flight of a bee, and perhaps the most inspiring of all, the unequaled aerobatics of the remarkable hummingbird. It is the nimblest bird of all, darting up and down, hovering, and even flying backwards, the only avian to do so. It has perfect freedom of flight, an ideal many early dreamers aspired to, though often in surreal ways.
There are legends of the flying carpets, the flying thrones of the Chinese, the Pegasus, the horses. All of these, interesting enough, all of them have one thing in common. All of them are vertical takeoff and landing machines.
This Renaissance painting of Madonna and Child may represent the first known application of vertical flight principles. The peculiar object in the Christ child's hand is a replica of an ancient Chinese toy, a rotor-bladed top dating back perhaps 24 centuries. And this may well have been the image that inspired that long-ago Chinese toy maker. Twisting leaf blades spiraling gently to earth. In the 2nd century BC, the extraordinary Greek mathematician and inventor Archimedes unknowingly demonstrated the physical principle essential to vertical flight. He built a giant rotating screw that propelled water from one agricultural field to another for irrigation. In the 15th century, Leonardo da Vinci understood that he could move air the way Archimedes moved water, and he used the theory of the screw to design a device that moves air downward to lift a machine upward in vertical flight. He called it a helicoid. 4 centuries later, in 1886, Archimedes' screw had evolved into this magnificent concept, the Clipper of the Clouds, a literary creation of novelist Jules Verne. It had an airplane propeller in front and dozens of rotors overhead. The leap from theory and fancy to a real vertical flying machine was not far off. It came with the Industrial Revolution. The breakthrough for all-man flight was the advent of the internal combustion engine at the turn of the century. It opened the door to all the dreams and schemes of vertical flight, and the first reported liftoff of a helicopter came on August 4th, 1907, only 4 years after the flight at Kitty Hawk. The honor went to French aircraft designer Louis Breguet. His contraption rose 2 feet in the air and hovered for 1 minute. But the pilot had absolutely no control of the aircraft. It had to be held in place by 4 men with ropes, or so it was reported.
In actuality, as it turns out, these mechanics were really lifting up all the time, and he really had human-powered help.
The first known true flight of a helicopter, with no ropes holding it in place, came a few months later by another Frenchman, Paul Cornu. He rose to the majestic height of 6 feet and hovered for 20 seconds. But there still wasn't enough power in early combustion engines to keep a helicopter hovering. Helicopters rely on sheer power to lift vertically, but power was only the first piece of the puzzle to be solved.
The first challenge was literally to lift vertically and to hang in the air a few feet above the ground. Now, once they had accomplished that, then of course people would start to say, well, now can you move forward and sideways through the air?
As well as power, there were still important aerodynamic pieces of the puzzle unique to vertical flight that had to be filled in, as many ingenious inventors discovered, often the hard way. Torque, for one. In a helicopter, when a rotor blade turns in one direction, the body of the aircraft must turn the other way, obeying Newton's law. For every action, there's an equal and opposite reaction. This counter-rotation effect is torque. One early attempt to solve the problem of torque came in 1913 with this twin-rotor helicopter built by Danish designer Jens Christian Ellehammer. It was a coaxial design, meaning both rotors were mounted on a single mast, a configuration that was used on many early helicopters.
The first sort of successful helicopters were the coaxial machines, where one rotor above the other, both turning in opposite directions, automatically counteracted the torque.
About this time, in an attempt to stabilize and control flight, a concept called cyclic pitch was introduced. This helped later pioneers like Frank Piasecki to design more controllable helicopters.
What you did was to change the pitch of the rotor blade as it went around its rotor mast, so that if the blade were made higher pitch here, it would go up, and if you change it to a lower pitch behind, it would go down. So the net result was that you, in effect, tilted the force in that direction.
For the pilot, cyclic pitch meant that to go to the right, you increased lift on the left blade, and to go left, you increased lift on the right. With cyclic pitch, the scene was set for putting the next big piece of the puzzle in place: controlled forward flight. Etienne Nomachen of France and Georges de Beauthézat in the United States were among the first to fly controlled forward flights in the early 1920s. De Beauthézat experimented with 4 different rotors and 2 propellers. In 1924, Argentinian designer Raúl Pataras Pescara introduced this elaborate helicopter, which set a record of nearly a half-mile. Pescara also introduced another important breakthrough for control called collective pitch. Collective pitch allowed the pilot to increase or decrease rotor thrust more quickly by changing the angle of pitch of the blades simultaneously, or collectively. But control of a helicopter was still primitive in the mid-1920s. It seemed the early pioneers would solve one problem only to discover another one waiting for them on the next flight. The final breakthroughs were still to come, through advances in technology, the sheer will to succeed, and the military needs of a world rushing headlong into World War II. The pioneers who built the early helicopters, on display here at the American Helicopter Museum in Westchester, Pennsylvania, were often scorned as eccentric, if not outright unstable.
As a matter of fact, I was engaged to a girl in one of my early days at college, and I gave her a ring. And her father, when he found out that I was going to go into a helicopter project, made her give that ring back to me and called off the engagement, which, thank God, financed the helicopter.
Pioneer Frank Piasecki could also thank this man, Juan de la Cierva, a brilliant Spanish airplane designer, for the ultimate success of helicopters. In the 1920s, Cierva experimented with a rotor blade on a propeller-driven airplane. He called the hybrid an autogyro. Sierva was not trying to build a helicopter. The rotor was to allow a conventional airplane to fly safely at lower speeds with less danger of a stall. The freewheeling wind-driven rotor would auto-rotate, letting the airplane land gently without power. Once again, man imitating nature. Other designers seized upon the idea, and auto-rotation has been a safety feature of helicopters ever since. But that wasn't Juan de la Cierva's only contribution. He discovered a phenomenon peculiar to rotor blades called dissymmetry of lift. A rotor blade moving forward into the wind creates more lift than the opposite blade moving away from the wind. And that imbalance of lift can roll the machine over as it begins flying forward. His ingenious solution was to put flapping hinges at the base of each blade on the rotor hub. Then, obeying the laws of physics, the blade advancing into the wind would rise slightly, while the retreating blade would dip, creating a balance in lift. Sierva's flapping hinge, yet another example of man borrowing from nature. Again, other designers quickly incorporated Sierva's breakthrough. One of the first to put the flapping hinge to use, nearly 30 years after his first historic flight, was Louis Breguet. On December 22, 1935, his state-of-the-art helicopter, powered by a mighty 420 horsepower engine, sped to an amazing world record 67 miles an hour.
Breguet was the first man that was able to demonstrate forward speeds of higher than 30 to 50 miles an hour in a helicopter.
More power, cyclic pitch, collective control, counter-rotating blades for torque, and flapping hinges for stability. The helicopter puzzle was finally coming together. In Germany, Heinrich Foka put his twin rotors side by side, eliminating the downdraft of one rotor over the other, which had made the lower blades less efficient. Control was so improved that Hanna Reich, one of the world's first female helicopter pilots, was able to fly demonstrations inside a large hall in Berlin. Meanwhile, there was progress in the United States. The pilot in this open-air contraption, wearing his trademark black Homburg hat, is Igor Sikorsky. He would be the man to put all the hard-wrought pieces together in one simple design. Simple, but not easy. To start with, he challenged conventional wisdom of the time that a helicopter had to have 2 or more main rotors to control torque. Sikorsky had attempted dual rotor designs many years earlier in his native Russia, and he insisted there was a much less complicated solution to torque, using a single main rotor.
The earlier pioneers that rotated one rotor against the other were the perfectionists. And Igor Sikorsky was the first pragmatist among them, who said that, well, we don't want to have a perfect solution, we just want to have maybe a sort of a sloppy solution, but it'll work. And that was the tail rotor. He had all of the great experts against him, because everybody said that this was the worst way possibly to ever design a helicopter. And yet Igor Sikorsky said no, that he felt somehow intuitively that the single rotor machine would eventually triumph.
His first experimental model in 1939 combined a tail rotor with a single main rotor and cyclic pitch. But early flights were less than encouraging. One nearly disastrous.
And Igor Sikorsky then decided, quite correctly, that he did not really know as much about that main lifting rotor as he thought he did.
He did not clearly understand phasing, the problem created by a delayed reaction between the control stick and the response of the main rotor. So he removed cyclic pitch and installed 3 tail rotors to do the job.
2 of them mounted horizontally, and their whole function is to lift the tail of the helicopter or to drop the tail of the helicopter. By lifting the tail, the helicopter flies forward. By dropping the tail, the helicopter comes to a stop.
But it was still too complex to be a practical flying machine. And Sikorsky labored through 2.5 years and 18 different configurations, only to end up back at step 1. A single main rotor, 1 tail rotor, and cyclic pitch. This time, cyclic pitch worked when he rephased the controls so the rotor head responded in the same direction as the pilot stick. That enabled the controls and cyclic pitch to work in harmony.
That last touch really was the breakthrough. And within 2 or 3 days, the aircraft was capable of flying at speeds of 65 and 70 miles an hour and coming to a hover, hanging perfectly in the air. It was literally that last step to perfect the helicopter.
On the eve of World War II, the military took an interest in the lighter weight, simpler design, and easier handling of Sikorsky's helicopter. In 1943, he began the mass production of helicopters, turning out nearly 400 that year. A new industry was born, and to this day, it bears the imprint of Igor Sikorsky's design.
Roughly 97% of all the machines that have ever been built since the VS-300 have been built in this single main lifting rotor configuration. Without a doubt, it was the breakthrough machine that established the industry.
Well, I take my hat off to all the pioneers and all the technicians that tried so hard to make the helicopter a wonderful, useful machine. And I put my hat on to join Igor Sikorsky when he flew with his Hamburg and when I flew with the PV-2 and its Hamburg, to greater successes for a great future.
Coming up, the future of helicopters and how they fly. Isolated in the swamps of South Florida, a high-security airfield, test flight center for the world's most sophisticated helicopter, the Comanche, and the pilots who fly it.
I thought it felt really good.
Nick Lapis is Chief Experimental Test Pilot for Sikorsky Aircraft, and he'll show us how a helicopter flies, using all the principles discovered over the years by the pilots who came before him.
Test flying helicopters, especially the Comanche, is a real thrill. I'm often asked, what is it that makes a helicopter fly, and how do I control it? Let me try and answer those fundamental questions. Come on. Today we're flying a Sikorsky S-76 model helicopter. It's a twin-engine machine designed for corporate transport. It's a conventional configuration of helicopter, and that means it has a single main rotor and a tail rotor for anti-torque. The main rotor provides lift, and the tail rotor counteracts the torque. Many people ask, what is it about a helicopter that makes it fly? This is the helicopter's main rotor blade. It's a form of a wing. Notice the airfoil curve at the top. Just as an airplane's wing has to be carried forward through the air at speed to develop the lift, the helicopter's rotor blade goes around the mast to develop that speed and therefore the lift. A helicopter can fly while it's standing still. We've all heard about the effects of torque. As the main rotor spins in one direction to create lift, it pushes against the fuselage and turns it in the opposite direction. The tail rotor counteracts that torque. Let's go to the cockpit and look at the controls. The basic controls of the helicopter haven't changed in the 60 years since Mr. Sikorsky laid them out. We talked about the tail rotor, and the pedals control the tail rotor. When I press on left pedal, I cause the tail rotor pitch to increase, and that increases its thrust, which points the nose to the left. Right pedal points the nose to the right. The cyclic pitch controls the swash plate and moves the rotor disc, so that when I push the controls forward, the swash plate tilts, and that causes the lift and thrust of the back side of the rotor to increase and the front side to decrease, which tilts the rotor. Therefore, when I push the cyclic, the aircraft tilts in the same direction. Pushing the cyclic forward causes the nose to tilt down and makes me go forward. To move backward, I pull the stick back, the rotor disc tilts up, and the aircraft accelerates rearward. Moving the cyclic to the left causes the rotor disc to tilt to the left, and that allows me to move laterally to the left. Moving it to the right is the same effect to the right. The collective pitch raises the swash plate and causes the lift of all the main rotor blades to be increased at the same time. So if I raise the collective pitch, the aircraft can climb. And if I lower the collective pitch, it descends. When flying the helicopter, the pilot coordinates the use of the controls to balance the forces on the machine, very much like you balance a broom on your fingertip. To lift to a hover, I just raise the collective pitch. The aircraft begins to rise and get light. I use the cyclic and pedals to find the right place to balance the controls and simply raise the collective into a hover.
The hover is the central point for our maneuvering. Everything's in balance. If I want the aircraft to move some way, I just have to upset that balance by using my control, and then the aircraft moves in that direction.
If we compare flying an airplane to riding a bicycle, then flying a helicopter is like riding a unicycle.
Recall that we discussed how the torque of the main rotor is countered by the tail rotor. If I raise the collective pitch and don't apply some increased left pedal, the aircraft will begin to rotate to the right. I'll let go a little bit. I'll stop it with a little left pedal here. Just put that left pedal in, and there it came to a stop. Imagine what it was like for the pioneers like Igor Sikorsky to face all these phenomena, and how to solve each one of these was really the crux of the problem of how to make the helicopter fly.
Hey, Nick, are you about finished down there?
Yeah, just wrapping up, Russ.
Yeah, hey, I wanted to check out that new low-level training area. Could you fly chase for me?
You bet. Why don't I take lead, you follow?
Okay. Did you look at the sky tonight?
What a sunset. Oh, what a view.
Yeah, what a great day.
But there are still secrets of flight to be found in nature that will help meet another challenge: how to combine the aerodynamics of a soaring bird with those of vertical flight. The answer to that challenge is a new breed of aircraft inspired by this powerful bird of prey, the Osprey. We'll see it next. After World War II, there were some pretty whimsical ideas about how helicopters might be used in everyday life, from commuting to work to bringing home the groceries. But it would take another war before the helicopter would be called into action. During the Korean conflict in the 50s, the military seized upon the helicopter's value in combat. In the 60s, helicopters revolutionized ground warfare in Vietnam, the helicopter war. Yet for all their deadly sleekness, even today's most advanced helicopters are limited in what they can do.
It became apparent that we had to find some different technology because helicopters do everything by brute force. We needed something with a little more finesse that gave us additional range, payload, and speed.
The primary mission for the Marines is as an early strike force, and the solution to their requirement was this: a part helicopter, part fixed-wing airplane called the V-22, V as in vertical. Its nickname is Osprey, a powerful hawk able to hover over its prey and strike like an arrow. The V-22 Osprey will give the Marines an important tactical advantage they call over-the-horizon maneuvering.
The proliferation of enemy weapons means that the ships that we operate from in the Marine Corps can't come in as close to the beach.
With the V-22, the Marines can stay hidden behind the curvature of the Earth, roughly 25 miles offshore. That gives them the protection of being over the horizon in the beginning phases of a conflict.
We use maneuver as a weapon, much like a chess player does. Hit them where they ain't is the football term.
The V-22 is known as a tilt rotor for obvious reasons. The rotors and their engine housings, called nacelles, one on each end of a fixed wing, can be tilted 90 degrees up or down. When they are down, the Osprey flies like an airplane. When they are up, it flies and hovers like a helicopter. The idea for this hybrid helicopter airplane has been around for many years, but as usual, theory preceded available technology. Bell Helicopters flew its first prototype tilt rotor, the XV-3, in 1955. In the 60s, the military took an active interest in tilt rotors, having learned not only the helicopter's value in Vietnam, but also its limitations.
The thing that you can't do with a helicopter is get long distances with good payloads for any extended period of time.
The military mission was clear, and with the basic aerodynamics proven, it was time to tackle the technology. One chief concern was the exceptional amount of power needed as the tilt rotor transitioned from helicopter to airplane. Piston-driven combustion engines in early models were too big and heavy to do the job well.
We didn't have the technologies in hand to build a tilt rotor that had any utility other than to fly. It couldn't carry payload. It was too heavy.
The solution came with the advent of much lighter and more powerful turbine engines. The advanced design of the turbine engine became an essential component of the next prototype, the XV-15.
And this allowed the turbine technology and tilt rotor technology to be combined. Extremely successful program. In fact, those aircraft are still flying today.
But even with lighter turbines, weight was still a problem for the V-22. Designers replaced many heavier metals in the fuselage, wing, and rotors with lighter and stronger composites of graphite, fiberglass, and other materials. That reduced not only weight, but also corrosion and cost. The next obstacle was in the flight control systems. The control mechanisms of airplanes and helicopters are different. They are not compatible for a smooth transition from helicopter to fixed-wing flight.
Let me give you an example. The rotor system on the tilt rotor in the hover mode operates very much like a tandem rotor helicopter. The rotors will lift and will tilt back and forth in order to control the aircraft in space. However, as the aircraft begins to move forward and move into the airplane mode, these controls gradually phase out, and airplane control surfaces, ailerons, rudders, and elevators control the aircraft when it's in the airplane mode. And when it comes back to the helicopter mode, the controls come back in and take over, and they become the primary control for the aircraft.
The solution was to replace mechanical linkages with a computerized control system, linking the pilot's controls in the cockpit to flight control systems throughout the aircraft. It is called fly-by-wire, and this is what it means to a pilot.
This thumb wheel switch right here, which the pilot activates with his left thumb, becomes the most powerful controller in the aircraft. With this controller, I can rotate my nacelles down to airplane mode or rotate them back to the helicopter mode.
Fly-by-wire made the V-22 Osprey much easier for a pilot to fly, setting the stage for a truly functional tilt-rotor aircraft.
It was not until we had added the other two technologies of fly-by-wire controls and composite materials to the turbine engine and tilt rotor technologies, and that is what has led to the successful V-22 program that we have today.
Maneuverability is another important aspect of the Osprey. It can hover, do turns around a point, fly sideways, and backwards, and within a matter of seconds be flying as an airplane at almost 300 miles an hour. A remarkable feat considering the size of the V-22. In fact, it takes only 12 seconds for it to convert from hover to full-flying turboprop airplane. But it would still take one more component to bring it all together: the glass cockpit, an array of computer-controlled displays.
In front of us now you see what we call the multi-function displays, the MFDs, a glass cockpit. This is the information that's displayed to the pilot that allows me to fly it. I can read my airspeed, my altimeter, my radar altimeter, vertical speed. Condensed in this one 8x8 square is all the information the pilot needs to fly the aircraft, keep it upright, and to go down range.
The glass cockpit means greater awareness of the flight environment for the pilot and crew. Also, the V-22 is the first rotorcraft with true anti-ice and all-weather capabilities. These features make flying in adverse conditions much safer. Another safety feature is in the Allison dual power system. If one engine stops, the other engine sends power to the failed engine's rotor. The pilot has less power, but maintains control of the aircraft, allowing him to make a normal landing. The V-22 can also be transported efficiently by ship. Its wings fold up for compact storage in a matter of minutes.
The basic V-22 can fly at up to 25,000 feet, so it can fly above the clouds just like real airplanes do, because in fact the V-22 is a real airplane. It has an unrefueled range of over 1,000 nautical miles, compared to a helicopter that may have 200 nautical miles. It also has the ability for in-flight refueling, which extends its range forever.
Range can be important, not only for combat purposes.
Disaster relief operations are something that we do quite routinely. A squadron sitting in North Carolina today, for example, could be in Central Africa tomorrow and could be delivering supplies and relief to the troubled people there 6 hours later.
Speed, range, and greater payload. The V-22 is complete. It was accomplished by the unprecedented cooperation of aviation giants Bell Helicopter Textron and Boeing Aircraft, along with many other contractors. They form 72 integrated product teams, from design engineers to shop floor mechanics, to master all the complexities of this most versatile flying machine. But still the question remains, is it an airplane or a helicopter?
This is an airplane that just happens to take off vertically and land vertically like a helicopter. But clearly, it is much more than a helicopter could ever be.
In fact, it's an entirely new species of aircraft, evolved from the combining of 21st century technology with all the elegant concepts ever conceived by the great dreamers of vertical flight. Coming up, the next evolution of helicopters, the smartest artificial hummingbird ever to be devised by human intelligence, a creature of the digital age.
Okay, we got a mission release. We're entering the operating area. I'm going to go weapons hot, lasers hot. Okay, I got line of sight. I got targets. Got a confirmation. Artillery is ready. Shot is out. Countdown. 3, 2, 1. Good hit. Good hit.
Shot. Good
okay,
shot.
We got artillery. Clear to remask.
Let's get out of here.
It's called the Comanche, a mysterious and powerful warrior combining speed, stealth, and digital power never before seen in a helicopter.
Okay, clears up. Good Delta T's. I'm scanning. I got bogeys. 2 o'clock.
The Comanche takes helicopter flight to a new level of sophistication. It was created to play a vital role on a modern battlefield, a high-tech battlefield requiring a high-tech response.
Today's battlefield is not linear like the old battlefield, not the strict lines we used to have. It's more open. We're facing a very sophisticated enemy that has access to the latest weaponry. He can see us with radar, he can see us with infrared, he can hear us, and he has very sophisticated mines today that can pick up pressure waves from helicopters.
The Comanche had to move like a shadow through this electronic battlefield and provide immediate, precise information.
Find the enemy, report the enemy, get that information to the right people on the battlefield.
To fulfill its mission, the Comanche required flight capabilities not yet seen in a helicopter, and it needed to be a true stealth aircraft, to see but not be seen. Stealth means not only evading the enemy, it also means preempting him, seeing him before he sees you, especially under cover of darkness. Comanche is designed to own the night. An advanced thermal imaging system called FLIR, forward-looking infrared, combined with low light level TV cameras, turns night into day and extends the pilot's eyes for miles over the battlefield.
Which means the Comanche can move in the battlefield, can find targets, and decide what to do with those targets before the targets know the Comanche's there.
And both pilot and co-pilot can survey the entire battlefield projected onto small television screens inside their helmets. They call it a heads-up display because the pilot never has to look down at a cockpit screen to fly.
That allows me to act as a quarterback on a football field, in that I'm able to look out at the battlefield and see the plays developing. As the plays develop, I'm able to orchestrate the battlefield, all from my position in the front seat of the Comanche helicopter.
The battlefield is spread out inside a very true-to-life simulated cockpit where pilots are trained to fly a digital helicopter. Adding physical reality to the virtual reality flight, the simulator itself moves in synchronization with the cockpit controls, giving the pilot a true seat-of-the-pants experience. The Comanche is designed to outfly any other helicopter in the air today, as demonstrated by these extraordinary maneuvers by an early test aircraft.
I've noticed right away that it has a tremendous amount of roll and pitch control power. The last time I felt that kind of roll control power was when I flew a T-38. It's really quite impressive. The way they've designed the power margins and the performance margins, the pilot will be able to use every bit of the envelope and fully exploit the agility and the maneuverability that the aircraft will have.
One of the reasons is tail power. The tail rotor of the Comanche does far more than counteract torque and provide directional control. It has added thrust that can maneuver the aircraft rapidly on demand.
If I was flying in my Comanche and all of a sudden I started taking fire from, say, these buildings on my right side, with the power of the fantail in the Comanche, I'm able to do a new maneuver that we call a snap turn.
The snap turn. It means the pilot can spin about on pinpoint, lock onto a target, and fire within seconds, and continue firing even while flying sideways or backwards, staying low, flying nap of the earth. All of this while the Comanche holds altitude automatically over hills and obstacles. The Comanche is a completely cybernetic creation, a new generation of helicopter, redesigned from the rotors down, incorporating technologies that had never been used in a helicopter before. The first thing you notice about the Comanche design is its odd shapes and planes.
The curves are gone, sharp, flat edges. The tail is not straight, the tail is actually cocked to one side. These look relatively unusual. They're caused by the need to keep the radar signature low. So the shapes are designed to reflect the radar waves from coming back to the antenna that sent them. So the antenna sends waves toward the Comanche doesn't answer back.
In fact, the radar signature of a Comanche is approximately 400 times smaller than that of a conventional helicopter. It is even less than one of the Hellfire missiles the Comanche carries. Something had to be done about them.
We hide the weapons inside a weapons bay. That means that the weapons are completely closed up while the Comanche's moving into the battlefield. The fact that the Comanche's radar signature is actually lower than the missiles it carries is an indication of how carefully we've designed it for radar signature.
Another stealth factor. The engine's exhaust has been cooled to virtually eliminate lock-on by heat-seeking weapons.
Unlike a conventional helicopter, the Comanche's exhaust is brought in through the tail cone, mixed with cool air and dumped out the bottom. The exhaust temperature is so low that the machine can't be seen by any heat-seeking missile.
As with all helicopters, engine power makes everything else possible. Two lightweight, powerful LH Tech engines that deliver more than 3,000 horsepower, yet weigh only 330 pounds each, are the key to the Comanche's performance. The engine had to be the equal of all the other 21st century components. Digital electronic controls continuously monitor the engines, automatically maintaining their operating parameters while diagnosing and informing the pilot of any problems. Automated controls greatly reduce the pilot's workload. They also mean fewer mechanical parts. In fact, it takes only 6 common tools to maintain the engines: super power, super sensors, and the stealth of a shadow. Now, what was needed was a computer to control it all. It has a supercomputer system that can process more than 1 billion bits of information per second and outsmart any other cyber weapon out there. Yet for all its remarkable sophistication and agility, the Comanche nearly flies itself with fly-by-wire technology.
There are no mechanical linkages from the control sticks in the cockpit to the various control surfaces of the airplane. It's all done with wires and digital computers.
The Aeroscout aircraft that I've previously flown required you to spend up to 70% of your workload just in physically flying the aircraft. With this thoughtfully designed digital fly-by-wire system, those numbers could actually be reversed. And whatever you pick up in savings from workload from flight control standpoint, you get to devote to the mission, organizing the battlefield.
And the pilot can also instantly share his view of the battlefield.
One of the key requirements of the Comanche was not just to collect information on the battlefield, but be able to transmit that information to the ground commanders or other aircraft, maybe people who are many kilometers away from the basic battlefield.
And I've got artillery. Okay, you want to send that back to the TOC? Okay.
The Comanche can immediately send data to jet fighters, AWACS radar aircraft, other helicopters, other weapon systems on the ground, and back to command centers where the battle is being directed. All while the Comanche stays hidden.
Part of seeing without being seen is to use the great maneuverability of Comanche to hide behind the hills, to fly at the treetop level, what we call nap of the earth, to stay masked from the enemy. When it gets to a target where it wants to collect data, it can pop up above the mask and collect all the data we need.
Okay, I got line of sight. I got targets. Okay. Looks like we got vehicles. Why don't you read mass? Coming down.
Then, while it's protected again, it can process that data and prioritize the targets. With its infrared sensors, target-enhancing displays, and computer bank data, the Comanche can distinguish friend from foe.
Okay, I'm going to scan, and I've got some trucks on a road. I got two large vehicles. Looks like they got UN markings, and looks like 4 Humvee escorts. Yep, positive ID on UN. Let's head on out to the next waypoint.
It can even tell if a man in the distance is holding a bazooka or a rake. Then, when an enemy target is confirmed,
Hey, we got a line of vehicles out on that bluff. I confirm the vehicles. Got a confirmation. Artillery is ready. Doors are deploying. I'm asking now.
the target is pinpointed and tracked by a laser beam.
Hey, here goes Hellfire. Shot is out. Got laser. Good hit. Artillery clear to remask.
Comanche is a tremendous fighting machine, and it will be able to take on anything the enemy has out there. But we hope we never have to fight this machine. We hope that we use it in peacetime only. And we hope that the enemy understands that this is not a system they want to go up against.
The Army sees the Comanche as a deterrent to war in the future. And beyond the Comanche, reality catches up with science fiction. The next UFO you see may not be unidentified. This flying saucer is the Cypher, a robotic unmanned surveillance rotorcraft now in the test flight stage. It's propelled by coaxial rotors placed in the center, protected from trees and other objects. It is remote controlled by computer, and its primary mission is to collect information using digital and infrared technologies.
If they had this in Chernobyl, it could quickly go in and give you the radiation levels, where things were leaking, everything else instantaneously. And if things go wrong, you've lost a vehicle. Nobody's been hurt. You look at the number of police forces in this country, if they could get a real-time aerial view of what's going on when they're rushing to a scene in their squad car or a fire engine running to a fire, Cypher can take a sensor in very close and monitor what's going on, so people can react quickly to the situation.
Meanwhile, the quest for the perfect rotorcraft continues. The Piasecki ringtail, a thrust-vectored configuration that can be adapted to existing designs, increasing thrust, speed, range, and maneuverability. The Canard rotor wing, equipped with a helicopter rotor that converts to a fixed wing during transition from hover to forward flight. But perhaps the first commercial use of new rotorcraft on the horizon will be a civilian version of the tilt rotor, shuttling commuters between urban vertiports.
what rotorcraft can do in the future is provide a method of transportation either from city center to city center or from the densely populated suburban areas into the major airport terminals.
The tilt rotor could also continue the long tradition of a helicopter's most valuable service.
I'd like to quote Igor Sikorsky, who said back in the 40s that if a person is in trouble anywhere in the world, a fixed wing can fly over it, but a helicopter can land and save that person's life.
In fact, helicopters are credited with saving more than 1 million lives over the years. Flying saucers, heliplanes, cybercopters, autogyros, whirligigs, and fantasies. All the legacy of Leonardo's helicoid and the visionaries who followed. And all inspired by nature. Would Igor Sikorsky have believed that in a single lifetime his sloppy solution would ever become so sublime? And is this what some pioneer of the future is dreaming up today? Is the bemused ghost of an ancient Chinese top maker watching over it all?